Hi, and welcome back to the Low Level Devel channel's Gameboy Emulator development series. In the previous video, we started by creating the structures for the CPU registers and instructions and loading them from the cartridge. In this video, we're going to start showing how to execute those instructions. So let's get started. Okay, so starting where we left off in the CPU.c, we need to make a new file now, which I'm going to call CPU_proc.c. This is going to be where we're processing the CPU instructions. So let's first, of course, include our header for the CPU. We'll say process CPU instructions. Okay, let's go back to our CPU.h and we'll add a couple of things here. So the first one is a function pointer, which we're calling inproc. So it's a function that returns void, takes in a CPU context pointer. So, and then we'll have a function called inst_getProcessor. So we'll get the function processor by the instruction type. So we can create a function for each instruction. Okay, now going back to our C file, let's start by saying inproc processors. So this is going to be our array of function pointers that will process instructions. Okay, you can think of this as like a map, a hash map, but we're just using an array in this form. So we'll start with proc none. So this is for the instruction type none. So we'll say static void proc none, and it takes a CPU context pointer. And for the proc none, we just want to fail once we hit here. Can print out some stuff like invalid instruction, and we can exit, let's see, exit -7 or something like that. So this is going to be in the case where we have hit something we haven't implemented yet, so we can kind of implement things as they come along. And actually, you know what I'm going to do is put these in brackets, so this way by default they'll all be null, and only the ones that I set up in the array specifically will be there. That way I don't have to try to put them all in the right order and everything. Okay, so we'll just create proc ld, and for now I'm just going to put to do on this one. We'll get into the actual implementation of it soon. So let's see, the next one we can do will be the instruction jp. So we'll create a proc jp. So this will be run whenever a jump type instruction is called. And now remember, the jump instruction can have some special conditions in which it will jump based on the CPU flags, which I don't think we've gone over very much. But if we go back over to the pandocs and look at the CPU flags, let's find it here. It's under, where is it? CPU registers and flags. Straight down here. Okay, so CPU registers and flags. You'll see we have these flags. Bit 7 is the 0 flag. Then we have the null flag, the half carry flag, and the carry flag. So specifically, the 0 and the carry flag are used for conditions. So let's go back and we'll create some defines for these. So let's see, we'll do a macro called CPU flag Z, and that's going to use the bit macro that we created in the common. So we want to get the bit number for F is going to be 7 is the flag Z. So bit 7 of our flags register. And for the carry flag, let me see, bit 4 is the carry flag. So this will give us the value of the 0 flag and the carry flag. So then we can do that inside of our check inside of our proc JP. So we'll say if check condition. This is a function we're going to create. So if the check passes, that means we're going to jump. So all we really need to do is set the register program counter to the value of the fetched data, because that's where we will have our value that we need to jump to. So let's include our emu.h. So doing a jump requires some CPU cycles. So we'll want to synchronize the PPU and timer. Alright, now we'll just create this static bool check condition. And then, so first we're going to grab the flags here. So grab the Z flag and grab the C flag. So now we want to switch the type for this. So the current instruction has a condition type, which by default is going to be none. And in that case, if there is none, then we want to return true, because that means we're always jumping. So now if C, that means we'll only jump if flag C is set. So we return C. If not C, then we only jumping if C is not set. And then likewise the same for the 0 flag. Okay, Z or not Z. And then otherwise we'll return false. It should never hit there, but you never know, so I'll just put return false at the end. Now, how do we actually use this array to execute these functions? So we've set up the array based on the type, and we've set up the functions to map them to. So let's go back to our CPU.c. So let's see, we had not executing yet. We'll get rid of that. So now we're going to say in proc, this is a function pointer, equals, what's the name of that function? So inst get processor. And what we're going to pass in is just the current instructions type. So now that should give us back either a function pointer or 0. So if it gives us back null, which, let's see what we should do for null. Let's just say no impl, because that'll execute, that'll exit the application, and otherwise we found the function, so we want to actually execute that function and pass in the pointer to the current context. Okay, so now let's go ahead and try to make this, and let's see, I hit some error. It looks like CTX should be a pointer. Yeah, I might revisit the way I'm doing this macro, but for now we'll just keep it like it is and fix it in the header. So let's see, it's in CPU.h up here somewhere. There we go. So this should be a pointer. And let's see, was there anything else that needed to change? Yeah, I don't think so. Let's just try to make it again. And inst get processor undefined reference. Oh, I don't think I created that function. So let's go to the CPU proc down here at the bottom, and I'll just get this from the header. and paste it in here. And this is a simple one, and really all we need to do is return processors type. So return the type that's mapped. Okay, so that built fine. Let's try to run it. DMG acid 2. Let's see, not yet implemented. Let's see. Oh, I didn't put I didn't put the no op instruction in here. This is an easy one to implement. So nop, we'll call it no op, and just copy this here and just change the name no op. And it doesn't do anything because it's a no op operation. So okay, so it executed no op and it executed the jump, it looks like, and then found another instruction. Okay, it's a little hard to see where it's at. We should make sure, let's change the way we're doing the logging a little bit. Let's see, we'll go into cpu.c. So we have fetch instruction, fetch data. I'm actually going to go back up here and remove this null check in the fetch instruction. Okay. And let's see, do we want to add it here? Unknown instruction. Segment fault. And I think that's due to the fetch data. So current instruction is null. We'll put that inside the fetch data. So if current instruction is null, we'll just return right away. This is just kind of a hack right now. And there you go. So you can see we actually jumped to the program counter 150 and got the F3 instruction there. This one actually jumped to 637 and then to 430. Okay, until it found one that it couldn't execute. Let's try a couple more. Let's try CPU instructions. And that one does the same, 637 to 430. So you can see it's executing a couple of these instructions so far. Let me see if I run it on one that I downloaded, Tetris. Okay, you know, that one has the AF instruction. If you remember, we were using that as XOR, I think. So we're using that in our little small sample program that I was going over. So to make things a little easier to debug, I'm pasting in a little lookup table here, so we can look up the instruction and get a string name for it. So it's just a simple array map type thing. So I'll put this in the header as well. So in our CPU step function, let's change the way that we're doing this logging. Let's see, we'll start with having the program counter. Let's see, just put CTX, or no, yeah, PC, our program counter. Then we'll put let's see, we'll put a string, say make its width 7 or something, and then this will be the actual instruction that we're executing. So we'll do inst name and regs dot, no, not regs, sorry, ctx dot current instruction dot type, or yeah, type. So that'll say that, and then let's give some bytes. So this will be the byte value of that code, and then let's read the next 2 bytes. And these next 2 bytes would be the next 2 bytes in the file after the opcode. They might not necessarily actually be passed to that opcode, but we're just printing them out so we can see them in case our opcode is using them. And how do we read? We use bus read, and we'll just do PC plus 1 and then bus read PC plus 2. And something's not going right with the syntax here. Yeah, I'll fix that later. Okay, so yeah, we have that fully done. So this is what the new format will look like whenever we execute an instruction. And actually, let's include some registers. Just I'm not going to do all the registers and everything for now. We'll just do a few of them. So we'll have the A register, the B register, and the C register. We'll just print those out before every instruction is executed. Okay, so for this we should simply do, oh yeah, remove that, ctx.regs.a, then .b and .c. Okay, we'll leave that unknown instruction there for now, I think. Okay, let's see if we can make this. Make clean and make CPU read reg. I think I might go ahead and fix that. So CPU read reg was complaining. Yeah, we just need to put that in a header somewhere. We can put it in cpu.h. Okay, that's much cleaner. If we run that against Tetris, oh, well, it looks like I forgot some returns. So let me add a slash in after this. Alright, so make, run it. So now you see we're at address 100, then 101, then 150, then 020C. The first is a no-op, a jump to 5001, which is 150. And the jump to OC02, which is 020C. And then an XOR, and that was the XOR on A, because we can see the opcode is AF. Those other 2 bytes aren't actually read by it. I'm actually going to change this to be left aligned, so we'll make that %-7. Looks like my terminal got stuck. I'm just going to add a new tab. So let's clear, make, okay. So, okay, my history's not there. So we'll take this same command. I'll just copy and paste it into the other terminal. Okay, so there you go. Now it's left aligned. So no op, jump, jump, and XOR. And we aren't modifying the registers yet, so they're all still showing zeros. Let's actually run it against some of these that I have in there. I do see a segment fault at the end of that. Let's try another one. And that one has a segment fault as well. So something's screwed up. Let's take another look. Okay, after a few minutes of troubleshooting, it comes down to this. Current instruction is null here, so we can't print that out. So let's go back to this fetch instruction. I think instruction by opcode has it in there. So going into that, we have that null check, remember, so we'll just remove that. And we'll add some better error handling later. But for now, let's just make clean. And clear that, make. Okay. Yeah, I added some extra debugging. Let me remove that. Cart.c. I added that while I was kind of troubleshooting. So let me make again. And now we see unknown addressing mode. So that's not a very good indicator of what happened, since we don't know know which instruction that actually came on. So what can we do to improve that? Let's see, unknown addressing mode. We could add the instruction opcode there. That's one option. Alright, so we can just do cur opcode. So we'll make, now we can see unknown addressing mode, and F3 is the opcode that had the error. F3 is the DI instruction, and that one actually disables interrupts, so that's a pretty common one to be called at the very start of the program. And actually that makes me think, we should probably have the default type as IMP implied. So we'll just change the order. Let me go back to the AM implied. So instead of having that down here, let's just move that to the top. So by default, any undefined structure or undefined instruction is going to have implied as the type. So now our logging looks a little better. So we have no op, JP, and then none. Okay, and we can see his F3 there. So that looks a little nicer. Now let's do a little bit more here. So I'm going to implement this DI instruction. And the DI is used to disable that master interrupt. So we're going to have a field int master enabled. So we can set that to false when the DI instruction is called. And if you remember, we just add that in our little array map there. I'm going to copy this, call it DI, CTX int master enabled equals false. Yep, make sure that name is right. Yep, it's right. Okay, and if you remember, we have to also add it to our instructions list. So F3 equals INDI. And since it's an implied addressing mode, we don't need to add that since it's default. Let's make it just nice clean and run it. So now you say DI ran, and then 3.1 is the next instruction, which we haven't handled yet. C3.1 looks like a load stack pointer. And since we haven't implemented that one yet, let's run a couple of other. We run it on the CPU instructions. Looks like it hits the same one. And the mem timing, same thing. Let me run it on my Tetris ROM. Let's see. So that one stops at the XOR function, and that one's not implemented yet. Now we did add it to our map. If you remember, we added XOR, its addressing mode is R, and its register type is A. What we didn't do is add it to, so what we didn't do is actually add a function to implement it. So let's go in our CPU proc. We'll just say, I'll just put it right after here. XOR equals proc XOR. And let's just copy the LD one for now. We'll make it a to do, just to see if it executes as expected. So we'll do make, run it again, and yeah, it executed. Well, let's actually go and implement it, because it's actually an easy one to implement. So regs.a XOR equals the context fetched data, and 0xFF, because we only care about the first byte of, or the bottom byte of fetched data. So then this one actually affects the CPU flags. So we're going to call a function CPU set flags. So CPU.regsA. And you see the first one is checked. And that regs.a should actually be regs.a equals 0 to check to see if it's 0 is what we'll pass in. I'll fix that in the code before I upload it. Let's see. And then the other three are set as zeros. CPU set flags. We're going to create this function. Alright, so now sometimes we don't want to modify a flag, and in that case we'll pass in -1. So if -1 isn't set, we're going to call that bit set macro. And for the first parameter, we're going to use our F register. So we can simply do ctx regs. Yeah, actually we're going to have to pass in the context, I think. Yeah, I might redo this one as well. But it allows us to run multiple CPUs at the same time, I suppose, if we do it this way. But yeah, for now I'll just do it this way. So ctx regs.f, and we want to set, let's see, the bit number 7 to the value passed in for z. And we essentially want to do this for each of those. So z, and then we'll do n, h, c, and those values are 654. And we're going to make sure we use this one here, NHC. Okay. That should be all we need there. And let's see, in our CPU, let's take a look. Yeah, so AMR, that's where it's going to load the fetch data. It's going to load it from the A register because we put register type as A. So that's where all this stuff is going to come from. Hopefully that makes sense. And let's, in our CPU init, let's actually set the default value for the A register, which is 0x01. That way we can see when an XOR is called, it's actually going to, let's see, oh, there's an error. I'm just redoing this bit set function as a if statement to fix that error. This should be else, and I'll put a semicolon here. Alright, make that again. And let's see, so let's clear and run it again. So you can see XOR actually changed the value of A from 01 to 00. Okay, I think that's a good stopping point. We've showed how to start executing some instructions, how to set it up in a more readable way. I've seen a lot of different emulators out there. We'll just kind of use one gigantic switch statement for handling the individual opcodes, which, yeah, I'm sure that's a lot faster, but you know, with the modern compiler optimizations, it's not really that big of a deal, and makes it a lot easier to read and to debug like this. And I like to keep this code simple so it's more readable than anything. It doesn't have to be super fast. It's going to be fast enough to run some emulation of some old CPU hardware for sure with no problem. So In the next video, I think we're going to just start focusing on adding more of the opcodes as they come along. We won't get to any of the video portion of it or LCD portion of it for a little while. I want to start getting through the instructions first. We will start getting to that when it's necessary, because eventually we'll get stuck in a loop waiting for data to be read from the PPU and things like that. So anyway, I hope you enjoyed this video and learned something from it. If so, like, comment, subscribe, join our Discord channel, which is in the description below, and thanks for watching.